Hello friends, we already have discussed about Bloch theorem, which gives us some generic form for eigenfunction of an electron in a periodic potential. In this lecture, we are going to study several features of Bloch electrons in detail, assuming a one-dimensional solid. The lattice points are arranged in a linear chain. Spacing between adjacent lattice points is A. The potential is periodic. We want to solve time-independent Schrödinger equation for a periodic potential U of x. Let us try to understand the nature of the periodic potential. Electrons in a solid is in principle a many-body problem. We have one electron potential describing the interaction of electrons with massive atomic cores. In addition to that, we also have pair potentials describing electron-electron interaction. We stick to independent electron approximation such that we do not consider electron-electron pair potential. All the interactions, including electron atomic core and electron-electron, are represented by an effective one-electron potential U of x. Designing such effective one-electron potential is a complicated problem and outside the scope of our discussion. Let us work with a 1D solid of length L is equals to n times A, where n is the number of lattice points and A is the spacing between the adjacent lattice points. In this diagram, n is equals to 10 such that L is equals to 10 times A. Note that the last point shown by the open circle is a periodic image of the first point. Since we have a lattice, we are dealing with electrons in a periodic potential, and eigenstates of the time-independent Schrödinger equation must satisfy Bloch theorem. Thus, the eigenstates are psi k of x is equals to e power I k x, which is a plane wave with wave vector k times some function uk of x, and this function has the periodicity of the direct lattice. That means uk of x plus capital X is equals to uk of x, where x is a lattice translation vector. A lattice translation vector is a vector which takes a lattice point to some other lattice point. For example, x equal to A is a lattice translation vector because this will take every lattice point to some other lattice point and nothing is going to change. Similarly, x is equals to 2A is another lattice translation vector because it will again take one lattice point to another lattice point and nothing is going to change. Now we can write psi k of x plus capital X is equals to e power I k. So in place of small x, I am just going to write x plus capital X. Okay. And here also we just write uk of x plus capital X. Now we know that this function small u, this has the periodicity of the direct lattice. So that means this term is equal to uk of x. So that gives us e power I k capital X times e power I k small x times uk of small x. But this is equal to psi k of x. So this term is psi k of x. Thus, we can write This is equal to e power I k capital X times psi k of x. And this is equal to what? This is equal to psi k of x plus capital X. Now, let us take some example. If we take the lattice translation vector to be A, then the eigenfunction must satisfy psi x plus A is equals to e power I k A times psi of x. The phase factor e power I k A cancels out when we calculate mod square of the complex function, and we get mod psi x plus A square is equals to mod psi x square. Similarly, if we take the lattice translation vector to be 2A, the eigenfunction must satisfy psi x plus 2A is equals to e power I 2ka times psi of x. The phase factor e power I 2ka cancels out as we calculate the mod square of the complex wave function, and we get mod psi x plus 2a square is equals to mod psi x square. Finally, if we take the lattice translation vector to be capital N times A, the eigenfunction must satisfy psi x plus na is equals to e power I n k a times psi of x, and mod psi x plus na square is equals to mod psi x square. Thus, the complex wave function does not have the periodicity of the lattice, as it differs by a phase factor from point to point. However, probability density must have the periodicity of the lattice, as shown here. Let us now focus on the K space. Since spacing between two adjacent points in direct space is equal to A, spacing between two adjacent reciprocal lattice points is equal to 2 pi by A. The reciprocal lattice points or G points are shown by red dots in this figure. The origin of the reciprocal lattice has a special name. It is called the gamma point. At the boundary of the box, psi of x must satisfy periodic boundary condition. That is, psi of x plus na should be equal to psi of x. Since we have a periodic potential, psi of x plus na also has to satisfy Bloch theorem, as shown here. For psi of x plus na to satisfy periodic boundary condition and Bloch theorem simultaneously, the phase factor shown here must be equal to 1. And this gives us the allowed values of k. Allowed values of k are small n divided by capital N times 2 pi by A, where capital N is the number of lattice points and small n is some integer. Allowed k values are shown by blue dots in this diagram. Thus, for a solid of length equal to 10A, allowed k points are small n divided by 10 times 2 pi by A. Distance between two adjacent allowed k points, which is same as the length occupied by a k point, is equal to pi by 5n. Distance between two adjacent g points, which is same as the length occupied by a g point, is equal to 2 pi by A. Length of the first Brillouin zone is also 2 pi by A. To get the first Brillouin zone, we have to draw perpendicular bisector of a line joining the gamma point and the B point. And the line will be approximately here. Similarly, we have to draw another perpendicular bisector of the line joining the gamma point and the minus B point, and this is where it will lie approximately. The first Brillouin zone is shown by the magenta shaded region in the figure. In this particular case, there are 10 allowed k points in the first Brillouin zone. Note that both k points and g points belong to the reciprocal space. Let us clearly understand their difference. Allowed k points depend on the boundary condition. If we double the length of the solid, we get a denser mesh of k points. For example, if we increase the length from 10A to 20A, as shown here, distance between two adjacent k points decreases by a factor of 2. For example, in case of L equal to 10A, distance between two adjacent k points is pi divided by 5A. However, if L is equals to 20A, then distance between two adjacent k points is pi divided by 10A. For L equal to 10A, there are 10 allowed k points in the first Brillouin zone. On the other hand, for L equal to 20A, there are 20 allowed k points in the first Brillouin zone. For very large value of n, k point mesh becomes so dense that we can consider it to be almost continuous. However, g points always remain discrete because g points does not depend on the boundary condition. As long as spacing between adjacent points in direct lattice remains same, g points does not change. Note that Bloch theorem is satisfied for every k point, and eigenfunction in a periodic potential can be written in this form for every k point. Before proceeding further, let us quickly review the main differences between the Bloch electrons and free electrons. In case of Bloch electrons, we have an effective one-electron periodic potential U. This is a one-electron potential because we continue to ignore explicit electron-electron repulsion term. That is, these electrons are still independent electrons, but these are not free electrons anymore. U equal to 0 is a special case known as the free electrons. In case of free electrons, eigenfunctions are plane waves. In case of Bloch electrons, eigenfunctions are plane waves times a function having the periodicity of the direct lattice. Psi of k is eigenfunction of the momentum operator, and h bar k is the momentum in case of free electrons. However, psi of k is not eigenfunction of the momentum operator, and h bar k is called the crystal momentum in case of Bloch electrons. In case of free electrons, we have only one length scale, L, the length of the box. L can be very large and we can take it as a macroscopic length scale. However, in case of Bloch electrons, in addition to L, we also have to consider interatomic distance A, which is of the order of 1 angstrom, and this is a atomic length scale. In free electrons, we completely ignore the underlying lattice. However, in case of Bloch electrons, we deal with real as well as reciprocal lattice. Periodic boundary condition is similar in both the cases. In case of Bloch electrons, this L is replaced with n times A. Because of periodic boundary condition, k points are discrete and allowed k points are similar in both the cases. However, again, in case of Bloch electrons, L is replaced with n times A. Since we ignore the lattice, we do not have g points in case of free electrons. So, we want to solve the time-independent Schrödinger equation for a 1D solid, where U of x is an effective one-electron potential having the periodicity of the direct lattice. The eigenstates are given by the Bloch theorem having the form of a plane wave times some function U of x, which has the periodicity of the Bravais lattice. When we consider a solid of finite length L, applying periodic boundary condition, we can get the allowed values of k. Let us see what we do not know so far. U of x is some generic function having the periodicity of the direct lattice. So, what is the exact form of eigenfunction psi of x? We do not know. We also do not know what are the energy eigenvalues of the Bloch states. Let us try to find these answers. Using plane waves of wave vector g, we can write the function u of x as sum over g u of g times e power I g x, where g is a reciprocal lattice point. That is, g is equals to n times 2 pi by a in 1D. This is related to Fourier series or Fourier transform, which we are not going to discuss in detail. Rather, I am going to show that if u is expressed in this form, then u is guaranteed to have periodicity of the direct lattice. Before proceeding further, let me discuss an important issue. We have g points as well as k points. Why do we expand u in terms of g but not in terms of k? Note that u must have the periodicity of the direct lattice. That is, u of x plus a should be equal to u of x. Let me prove that if we expand in terms of k, we do not get some u which has the periodicity of the direct lattice. If we write u using k points, then u of x is equals to sum over k u of k e power I k x. Now let us try to find u of x plus a. This is equal to sum over k u of k e power I k x plus a, which we can write as sum over k uk e power ikx times e power ika. Note that this part is u of x. Thus, for u of x plus a to be equal to u of x, e power ika must be equal to 1. Now, let us see whether we get this or not. We know that k is equals to 2 pi n divided by n times a. Thus, k times a is equals to 2 pi n divided by n. In that case, we see that e power ika, this is not equal to 1. So, e power ika is not equal to 1. In that case, we cannot say that ux plus a is equals to ux. Thus, if we expand u using the k points, the potential does not have the periodicity of the direct lattice. Now, on the other hand, if we write u using g points, then we get u of x is equals to sum over g ug e power ikx. Now we write u of x plus a is equals to sum over g u of g e power I g of x plus a. And we just write it as sum over g u of g e power I gx times e power I g a. Note that this is again just equal to u of x. Thus, if e power IGA is equals to 1, then we can say that u of x plus a is equals to u of x. Let us check that. So we know that g is equals to 2 pi n divided by a. That means g times a is equals to 2 pi n, where n is an integer. Thus, we see that e power IGA is indeed equal to 1. And in that case, we know that u of x plus a is equals to u of x. Thus, for u to have the periodicity of the direct lattice, we must expand it in terms of g, not in terms of k. Thus, a periodic potential u of x can be expressed in this form, where g is a reciprocal lattice point. Note that for every g, there is a minus g. For example, for b, we have minus b. For 2b, we have minus 2b, and so on. Thus, we can write u of x is equals to sum over g greater than 0 u g e power I gx plus e power minus I gx, where these two g's are always positive. And then we can write it in the form of 2 times sum over g greater than 0 ug cos of gx, because e power I theta plus e power minus I theta is equals to 2 cos theta. Note that we have used g greater than 0. So how about this point where g is equals to 0? We ignore the term u0 because it provides a constant potential in the direct lattice. Making u0 equal to 0 does not make any qualitative difference in the periodic potential. Thus, we can make u0 equal to 0 without any loss of generality. Note that u of g is real. This can be proved using symmetry argument, but I shall skip the proof. There are many g points. How many do we need for the sum to converge? Fortunately, not too many, because as g increases, u decreases rapidly. For example, in case of Coulomb potential, u of g varies as 1 by g square. Thus, contribution of u of g decreases quadratically with increasing g. For very large value of g, u of g will be so small that it will hardly contribute to the periodic potential u of x. Using a simple Python code, let me show that we get a periodic potential by writing u of x in this form. For simplicity, we keep only two terms in the sum, g1 and g2, such that u of x is equals to 2 times ug1 cos g1 of x plus ug2 cos g2 of x. Let us take a equal to 1 such that the lattice points are located at -2, -1, 0, 1, 2, etc., as shown by blue circles in this diagram. Since the atomic cores are positively charged, negatively charged electrons will see some highly attractive potential near the cores. As a result, we expect the potential energy to be minimum at the lattice points, as shown here. The attraction decreases as the electron moves away from the lattice point. Thus, we expect the potential to be maximum in the middle of two lattice points, as shown here. Since a is equals to 1, g1 is equals to 2 pi and g2 is equals to 4 pi. So this is where we define G1 equal to 2 pi and G2 is equals to 4 pi in the code. We assume that UG goes as 1 by G square, such that UG1 is equals to -1 and UG2 is equals to -1 by 4. After multiplying UG1 and UG2 with the factor of 2, we put -2 and -0.5 in the code while defining the potential in the code. Let us run the code. The blue line shows the periodic potential and vertical red dashed lines show the location of the lattice points. Let us take some other value of wave vector. For example, (4 pi by 5) and 5 pi by 5. And then we generate the plot of u of x again. The first figure from the left shows the potential ux when it is expanded in terms of 2 G points. Red dashed lines show the location of the lattice points. As expected, the potential has the periodicity of the lattice. Potential is minimum at every lattice point and it is maximum in the middle of 2 lattice points. The second diagram from the left, that is this one, shows the potential ux when it is expanded in terms of 2 allowed k points. Clearly, the value of the potential is not equal at every lattice point. For example, at this lattice point, the value of the potential is this, and this is not equal at any other lattice point. Thus, if we expand u of x in terms of allowed k values, we do not get a potential having the periodicity of the lattice. In conclusion, Fourier series expansion of ux must be done in terms of g points to ensure that ux has the periodicity of the underlying lattice.